A good Friday. I believe I need this reading week badly. How many of you need this reading week badly? Yeah, I'm the same. Okay. It's not just you. I also need. How many of you are going away? Come on, really reading week. I mean, away as in going home or to Barbados. No Barbados. No. Okay. So today I'm going to carry on with the introduction of sharing stress. Where we finish off, I found this on internet. It was so funny. Right? It's absolutely excellent. You get that? Okay, no, it's just and I was wondering who is Woodstock, you know? And I thought Woodstock was what's the little Yoda called? Gogu, right? I thought Woodstock was Gogu, but when I zoom in, that's not Gogu at all. But anyway, excellent comedy. Right. So where we last lecture was, I think I threw too much on you guys. Okay, was a lot. We look at fracture, we link element, chalk, mole circle, chalk, and going back to the element, right? So you guys can now relate mole circle to the real world to detect the orientation of the fracture. Then I show you guys this image to explain to look at how a beam has been fractured under controlled shear, and we realize that the surface we analyze is the one highlighted in yellow. Why I say that is because the first moment of area we calculate based on which surface? The yellow surface. The second moment of area also based on the what? But on the yellow surface. But fracture occur where? The pink surface. Okay, I repeat again. Fracture occur in a pink surface. To grasp this topic well, you need to understand why things happen that way or not. You get very what? Resistance. Yes or no? Right? We are what? Mechanical engineers. We know V equal to IR. And we see. No, right? We have to be able to visualize. So this topic, very simple. 2 formulas, 7 rules. If you don't obey these 7 rules, this topic is close to impossible. Are we clear? Okay, so you have to obey these 7 rules. Okay? Right. So again, now this happened last week. I'm going to take this image over here. Paste this here. And then I'm also going to take the fracture surface. I'm going to paste it here. Okay. So now we know from this transformation over here, the analysis carried out is on the YZ plane cross-sectional area. Right? i.e., when we apply our first moment of area, we do Q is equal to A Y bar. The A is based on the area on the yellow plane, okay, which is a likewise the second moment of area For this case, we do second moment of area, which is equal to IZZ. So I just write down the general formula, BD cubed over 12. Again, it's on the what? Yellow surface. The A and I are taken on the yellow surface. However, fracture pattern is along the exact plane. Okay, so the pink, right? The pink is our what? Exact plane. Based on this image that we see over here, right? Based on this image we see over here, the transformation looks like this. This is our X, this is our Y, and this is our rotation about Z. Okay. So by looking back at the fundamentals, okay, we know when we sketch our stress strain curve, it can be normal strain or shear strain. It can be normal stress or shear stress. We tend to get this trend. Okay, so this is where fracture will occur. Over here, if I divide this into two, this is our plastic region. And over here, this is our elastic region. So, i.e., most material to induce fracture, we need to what? We need to induce sufficient epsilon F, means strain to achieve what? Fracture. Okay. Now, let's imagine, okay, we are going to do a schematic of a cantilever beam. Okay, we're going to do a schematic of a cantilever beam. So now we have a beam, and this beam, what we are going to do is we are going to put this beam in layers. Okay, we are going to have this beam in layers. So over here, this is our layers. Okay, the layers, each layer can slide, okay, can slide over one another. Okay, this is just a schematics. I want you to visualize something. Okay, so now we are going to have a shear force acting in Y, and I'm going to have our transformation. This is X, and this is Y, and this is rotation about Z. So we are going to have a what? We're going to have a deformation. Deformation, and it's going to deform in such a way that it's going to deform in a set phase manner. So in a set phase manner, next we're going to sketch the deformation pattern. So the deformation pattern looks like this now. Okay, so this is how the structure will deform. And this is, I'm going to copy, I'm going to paste. Okay, and this is how the structure is going to deform. And then I'm going to, I wonder would this work? Okay, if it doesn't work, it's embarrassing, but it's okay. Again, we are not doing a cooking show. Now, this deformation is exaggerated. I repeat again, this deformation is exaggerated. Probably I did too much layer, but it's okay. You don't no need to copy, okay? Just I will post this on Avenue to Learn. You can see it better. Okay. Just take my image and okay. Okay. And then these are all what? 90 degrees coming down. Hey, zoom. Okay. Maybe one too much layer. Okay, this layer will stop here. Okay, this layer was too much. Okay. So what you see now, okay, what you see now, if we were to expand this view, it looks like this. Right? It looks like this. So what you see is over here, you see a what? Delta. Yes or no? Right? Whereas the thickness did not really what? Change at all. So now it's slipping, and this slippage, right? So what we have over here, the delta is the slip, okay, parallel to the layers. Okay, it is this slip that it will induce the what? The slip, right? The slip will induce a delta, and hence you have epsilon, you have a strain in the direction parallel to the layers. So the phase which we analyze, right? Whereas the layer, the longitudinal layer, or the layer that's along the ZX plane, you see a what? A displacement. That's what you see a change in what? You see a slip. Okay, and when there's a slip, there's a strain. Okay, so some of you say, Eugene, so what? Yes or no? Right? So what? Right? So when there's a slip in that direction, it means there's a what? There's a stress. That is why the slip over here, the delta over here, is along what? If you go back to the origin, right, it's along the what? XZ plane. We clear? It's along the XZ plane. So in this context, I don't think we can still see the relationship until I draw the next diagram. Okay. Now, the next diagram, you guys have seen it before. We are going to go back to the element. Let me get the diagram. Okay. Let me. Okay. So that's slip. Now, and let me get the original. Let me also get the original. The next thing that I will sketch the next thing I will sketch is I'm going to sketch the elements. So we are going to look at element configuration in terms of pure shear. Now we know if this is our element and this is our transformation, we know that on the left hand side